In this lecture, I'm going to tell you about similarity of matrices. So to understand this, let's start with a vector space V and T linear map from V to V. So we'll assume that V is a vector space over the field K. That's the underlying field. And let's also have a basis U1, U2, Un, a basis of V. So this V is an n-dimensional vector space over K. Then we can write down the matrix of T with respect to this basis U1, U2, Un. So if A is the matrix of T, with respect to U1, U2, Un, this means that TVJ is given by the expansion of TUJ is given by summation Aij Ui. I goes from 1 to n. With this identity we can also write in a slightly more slick form. Let's form a vector whose coordinates are themselves vectors. So a row vector whose coordinates are the basis vectors U1, U2, Un. And then what we are saying is that, let me just move this to the side, we can form the other row vector, its image under T. So TU1, TU2, TUN. This vector is equal to this vector times the matrix A. So this identity here, which I've written in vector form, is equivalent to the identity above, which can be taken as the definition of saying that the matrix of T with respect to the basis U1, U2, Un is A. Okay, now let's see what happens to A under a change of basis. So suppose we have another basis. Then we can try to expand these new basis elements in terms of the old basis. So let's say Vj is equal to some I goes from 1 to n, xij ui. So this equation we can write in terms of this vector notation as v1, v2, vn is equal to u1, u2, un times x. So this is the same as saying that Vj is summation xij ui. Okay, and now I want to understand the basis of the matrix of T with respect to this new basis V1, V2, Vn. So now if you look at T Vj, well, this is by linearity, this is summation I goes from 1 to n xij t ui. So we can write this identity as in vector notation as tv1 tvn is equal to tu1 tun times x. Okay, so now we are ready to write down the basis of A with respect to the new basis. So what we need to figure out is how to write tv1 tvn in terms of v1, v2, vn. Okay, so tv1, tv2, tvn is, recall, it's this tu1, tu2, tun times x. So this is equal to tu1, tu2, tun times x. But now we know what tu1, tu2, tun is. Over here we've written it down. It's u1, u2, un times A. So we have times A times x. And now let's try to express this u1, u2, un in terms of v1, v2, vn. We've seen that v1, v2, vn, this row vector of vectors is this row vector u1, u2, un times x. So we can invert this and write that u1, u2, un is v1, v2, vn times x inverse. So we have v1, v2, vn times x inverse ax. So here if we call this matrix B, then what we get is that the matrix of D with respect to the basis v1, v2, vn is B. And this motivates the definition of similarity. So suppose we have two matrices A, B in M and K, and by n matrices over any field K, we say that A is similar to B so we will use the notation for this A, and we'll just draw a squiggle here, B. If there exists a matrix X in GL and K. So this matrix X that we had going from the basis U to the basis V has to be invertible, because we can go back from the basis V to the basis U by its inverse. So this matrix X is in GLK such that B is equal to X inverse AX. And the point is that two matrices are similar if and only if they represent the same linear transformation with respect to different bases. With respect to possibly different bases. And this you can easily see that the similarity is an equivalence relation. Now, because two matrices are similar if and only if they represent the same linear transformation, any property of a matrix that you define with respect, which in terms of the linear transformation corresponding to a matrix, will not change if you replace a matrix by a similar matrix. So for example, so here's the sort of meta theorem. Any property of a matrix A that is defined in terms of its linear transformation So if you have a matrix A, you can define TA from Kn to Kn given by TA of V is equal to AV. So here we think of V as a column vector, and so you just multiply A on the right by V to get a linear transformation. So this is the linear transformation corresponding to the matrix A is invariant under similarity. That means if you replace A by a similar matrix, then this property will not change. So that's so for example, so if you take the rank of a matrix A, well, you can define it purely in terms of the linear transformation TA. This is the dimension of the image of TA. So if A is similar to B, then rank of A is equal to rank of B. Okay, we can define a matrix to be idempotent. A is idempotent if TA is equal to TA squared. So this is the definition of idempotence. It's defined purely in terms of the linear transformation corresponding to A. So if A is idempotent and A is similar to B, then B is also idempotent. Okay, so similarly you can talk about nilpotence, that is some power of A is 0 or something like that. Here's a somewhat more interesting one. So let I be the ideal of all polynomials Pt such that P of Ta. So given a linear transformation and a polynomial, so this is a polynomial in Kt, maybe let's specify that, P in Kt such that P of Ta, so this is again a linear transformation. So if P is A0 plus A1t plus so on, then P of Ta is A0 plus A1ta plus A2ta squared and so on. So to look at all the polynomials, that PTA is the zero linear transformation. It's a zero linear transformation from B to B. Then this I is an ideal. In Kt. And so since Kt is a principal ideal domain, this ideal I is generated by a single polynomial. And if we want to make that polynomial unique, we can take it to be monic. So there exists a unique monic polynomial QAT such that I is the ideal generated by QAT. This polynomial QA is called the minimal polynomial of A. This is called the minimal polynomial of A. Now this polynomial is defined entirely in terms of the linear transformation TA. So what we have is that if A is similar to B, then the minimal polynomial of A is equal to the minimal polynomial of B. Similar matrices have the same minimal polynomial. Okay, and there are some more properties that are invariant under similarity. So for example, trace. So we know that trace of AB is trace of BA for any two square matrices A and B. So we can show that trace of X inverse AX. So if B is similar to A, then B is X inverse AX. We can use this trace of AB is trace of BA by taking this to be the first matrix A and this to be the matrix B. And now we reverse the order. So what we get is this is trace of X times X inverse A. So this is the second matrix here and this is the first matrix here. But that's just the same as X times X inverse cancels, so trace of A. So what we get is if A is similar to B, then trace of A is equal to trace of B. We have a similar thing with determinant. Determinant of AB, well, it's determinant of A times determinant of B, which is the same as determinant of B times determinant of A, because the field K is commutative, and so this is determinant of BA. And by the same kind of argument, you get that if A is similar to B, then determinant of A is equal to determinant of B. And let's look at the last most important invariant of similarity class is the characteristic polynomial. Recall that the characteristic polynomial of A is defined to be the determinant of Ti minus A. So this is a matrix whose entries are themselves polynomials in T. But if A is similar to B, then the matrix Ti minus A is similar to the matrix Ti minus B. And so you can show that if A is similar to B, then chi A is equal to chi B. So we see that a lot of important features of matrices do not change under similarity. And this is because similar matrices represent the same linear transformations. So we can ask now, is there a way to decide whether two matrices are similar or not? And we can also ask, how do I classify all matrices up to similarity? Okay, we will see the answer to both these questions in the next lecture.